Hi everyone and welcome to a new video about control system topics, and we continue with the subject of stability and in particular with the situation of Routh-Hurwitz stability criterion, and it is our example number 7 already. What we do is we will check using our calculation what the stability is of a given system, and we will verify our calculation using the simulations, and we will do that in MATLAB. So let's look at our example. What we have is the following system. We have 4 systems in total. We have the gain K, we have a system G, we have a system P, and we have another system H. So these are given here, and again the similar question. Determine the value of the K, which is here the controller, such that the closed loop system is stable. Now the G is here a first order system, 12 over s plus 4, which has a stable pole at -4. We have a P, which is 2 over s, which is a pure integrator, and the H is also a first order system, 7 over s plus 7. It has a pole at -7. So all of these systems are stable. In this configuration, we would like to keep it stable in its feedback configuration. So what we do is we will start again with the characteristic equation. So we will determine the characteristic equation of our closed loop system. Now, since this system is again a little bit complicated, I will make again intermediate steps to determine the actual closed loop system. So let's first look at the inner system, which is actually this. So let me give that in this area. So this part I will call a new transfer function. I will just call it A. That is actually very simple to calculate. What you see is there's a K here in cascade with the G, which is just a multiplication, K times G. And this is added to the P, so this system plus this system will be actually, will produce a signal at this point. So I can say K times G plus P is actually our A. So you don't use here the Mason's gain rule, remember. Mason's gain rule is used when you have a negative or positive feedback. So it is not there is no feedback here actually. So what we have, A is then K times GS plus PS. If I now substitute the given values here, I have the following situation. And if I now a little bit simplify this, I get the following expression. Again, I would like to keep this in one fraction. So collecting the terms, I have now the following expression. I can even more simplify this by taking a 2 as a coefficient out, and I will have the following expression. So this is now our expression for the transfer function A, which is now here given in the diagram. Now, what is now this system in a simplified form? How can we draw this? Now, we can make a drawing, a nicer drawing, which is much simpler and much compacted. What you see is there's an A here, which is fed back, and then we have that H, and that is then fed back here in a minus form in this summation point. So this system is much simpler than that system. Now again, we can continue with the analyzing a transfer function using now the Mason's gain rule. Now let's first define where the closed loop system is. That's actually in this region, and we call this T. So, and again, if I now continue, again make a simplified drawing, I get this, the simplified form, so even more simple than this one. It means actually you have an input, you have an output, and only one system. And this system we would like to determine, and from this system we would like to determine the characteristic equation. So let's look at now the outer loop, so actually this total system. So the outer loop will give us the following transfer function TS, which is now using the Mason's gain rule, which is actually showing as follows: forward path, all the elements in there, which is in this case just 1, divided by 1 plus the loop gain, which is A times H. Now that's shown here. Now if you now substitute the values, we have determined the A. We have now here the A completely, 1 plus A again, times H, which is shown here. Now if you simplify this even further, you will get this one. You can make another step, simplify this, and it is the final form. I want, of course, my expression of my transfer function, the denominator of that, in a polynomial form with higher order and then up to the lowest order. Why? Because then we can use that characteristic equation directly in our stability, in our table of the Routh table. That's actually the reason why I already have this expression. So our characteristic equation will be given by the denominator of that closed loop system, TS. So we have now our correct equation. This is now given here in a nicer form. So we have now the situation here. So let's look at the next step, which is generating the row table to define or determine the gain k for a stable closed-loop system. So for a third order system, we have, again, I can now show you the summary of this situation. We have the correct equation, which is shown here. This is a third order polynomial, which is in general form. I can now again determine like terms. A3 is just 1 here, A2 is 11, A1 is 14 times 6k plus 3, so I can also write it down, and A0 is just a constant, so it will be 56. Now, if I now just substitute the values in here, and then determine, again, using the first column, the stability of the system, then I'm done. So, first look at the first row here, because I need B1, B2, B3, and C1, C2, C3, but of course I'm interested especially in the first column. So let's first look at this row of s to the power 1. First do that. Now again, we use the familiar formulas for our B1 and B2, B3, and later on for the others. So this is actually the expression for B1. Again, you make a matrix of these 4 elements, and you determine the determinant of that one, you put a minus sign, and you divide by the A2, which is on top of the B1. Now you do the math. Actually, you substitute the values of coefficients here, you get this expression. That's nice. Now for B2 in a similar form, you get a 0, and for B3 you get a 0. Remember, it is actually the same for the first column actually, but you shift in the B1, you use this column, and for B2 you use this column, and for B3 you use actually this column, which is for sure 0, and that will all produce 0. So we will only have the B1, which is non-zero. And in similar form, we can now make the calculation for this row, which is shown here in a similar form. C1, again, we have done this many times in the previous video, so I will not go into too much detail, but you will see that there's a similar calculation, and this will be 56. Now we have now the C2 and the C3 also in a similar form. Again, all of them are 0 except the C1. So C1 and B1 that are non-zero, and that is actually what I wanted, so I can now just substitute the values. So what we have is, if I now substitute the values here, using also the coefficient of the characteristic equation, I have this one. Now I will now check the first column to evaluate the stability of our system. So let's do that. Evaluate the value of k for stability. Now, from the root table, we see that we require the following condition to have no sign changes in the first column. Which condition is that? Now, if I want no sign change in this column, this is a positive number. This is positive, so I want to keep this positive, and this is already positive, so I want to keep this positive. So this must be larger than 0. So this is actually the only condition here. So if I rewrite this, make it simplified, so I will place this 4 on 6 divided by 11 to the right side of the inequality, so I get this one. Now, if I now simplify that even more, I divide by 84, and this is actually what you have in an exact form. And if I now just simplify this or make an approximation, you will get approximately 44, so minus 0.44. That means the following: this closed system is stable if you have a value of k which is larger than minus 29 divided by 66, approximately minus 0.44. But now let's ask another question, because that will be also discussed in the next step in the simulation. What happens if now k is exactly minus 29 over the 66? Now that's actually what we also discussed in previous videos. Let's check it again. So we will take this table, and we will now substitute the k value for minus 29 over 66. So let's look at it. What happens if k is minus 29 over 66? This is what we had. This is a table. We have determined now the value of the k for stability. If I now just use that, just substitute the k is equal to that, minus 29 divided by 66, I get actually here a 0. Does this row, the column, has now a 0 in it, and that, you can see it here, And that suggests actually there's a marginally stable system. That means we will have a sustained oscillation at the output. Now, we will now also determine the characteristic equation for determining the oscillation frequency. So that was not really the part of the question, but it's really interesting. We have now determined actually just what a value of k must be to have a stable closed system. But let's look also in addition to the part of oscillation frequency. For that, you will take actually the row above your element where there is a 0. So you will look at the row where there is s squared. Now you will develop your auxiliary polynomial, QS in this case. It is most time called PS, but PS is already used in our example, so let's use another letter. So QS. And QS is developed as follows. QS is 11s squared plus 56 s to the power 0, which is just 56. So this is actually the auxiliary polynomial. We have now this. And if I now equate this to 0, I can determine from that the oscillation frequency. So if I now do that, 11s squared plus 56 is 0. Now I have 11 divided by 11 left and right side. I get this expression. If I continue with the simplification, s squared is minus 56 over 11. And now s will be plus or minus j of the square root of that one. It is j because we have a square root of the minus 1, so it will be taken out of the square root. This is a pure imaginary pole or pure imaginary solution. So this is also called omega n, natural frequency. So this is plus or minus j omega n. Now the minus value of that one is not really interesting, and we look only at the value of that. So we don't care about now at the imaginary part of it. Of course, that tells us that there is a sustained oscillation, but the omega n now, we will only take the number here, and that is our oscillation frequency. This omega n is this value, and this is approximately 2.26 radians per second, and this is our oscillation frequency given in radians per second. And what is now the oscillation period? Now that is of course quite easily calculated using this familiar formula. This is the period, just time is equal to 2 pi divided by the omega, which is now in this case omega n. And if I now substitute the values, 2 pi divided by the square root of an exact form 56 over 11, I get approximately 2.87 seconds. Now I will now check also this situation. So I will substitute in the next step in the simulation the gain k, and I make the k minus 29 over 66, and I will now check that the oscillation frequency is indeed 2.78 seconds. So let's jump to the simulations. So let's continue with our simulation. In this simulation we will check our findings of stability in the calculations. Now I have now developed a script here. I've collected all the necessary elements in here. What we have also done in the previous videos, we define first a Laplace parameter s, which is given here. I will run this script shortly. I have now the open loop system here. G is equal to 12 over s plus 4, which is what we had. And I have now the integrator also as p, and we have the other transfer function h also given. Now I have now purposely given the value k, which is now the edge of our stability. The k must be larger than this number, so minus 29 over 66. That is actually the edge of stability. This will result in a marginally stable system, and we will now check it also. Now we had the a, which was given as an intermediate transfer function, which was given k times g plus the p. We have done this also as an intermediate step. Now the t, which is now the total closed loop system, is the feedback of a, which is the forward path, and then comma, the following is the h, which is the transfer function in the feedback loop, and a minus 1 just to mention that this is a negative feedback. This is not really necessary. The MATLAB understands directly that this is a minus 1 if you forgot that. Okay, now, and this is just a time to plot the step response. It's not really necessary, but I did that to have a nice plot. and this is the command to plot the step response. So if I now just run this, let's do that. Run. So we run this. I get the following situation. As you can see, we have now run this script, and this is the plot. Let me make it larger, and I will now check that we've already verified now that this value of k will result in the oscillation. So I've now verified that this is a marginally stable system. What we also did in the example was we have also calculated, let me make this clear here, we have also calculated the oscillation frequency. It was 2.78 seconds. I can do that by checking the period also here. So I mean the period which we have verified the oscillation period. So that we can now determine also that from the plot we can check at the two maximas. So I can place the element here, a label, which is at the top, and which is has a value of 2.4 at 1.68 seconds. So if I now do it also at the next maximum value, which is approximately here, somewhere here, it's not really that accurate to determine, but let's say it is here. Now I have now the following point. Of course, you can make it much more accurate by taking more points and then divide by the number of periods you have in your plot. But let's do it in this case because I think it is accurate enough. I have now 4.48 for this point as a time, and for this point I have 1.68. So if I now make this a little bit smaller and place it here, and I also can place a grid here. So what can I say? I can say, okay, now let's calculate T oscillation. T oscillation just from the measurement from the step response. So that is 4.48 I mean, minus 1.68, which is 2.8. What we had was 2.78, which is really close, because I just, of course, look at it with my cursor here, and it is maybe not really that accurate. So I've already found that the oscillation frequency is correct. Now, if I now check also the stability, why must the k larger than this number? Maybe it must be a smaller number. So how can we check that? You can also check that by using R locus on this transfer function. You can also say, now I just type a new value for k. K is equal to, let's say, a larger value of this one. So I will make it just 1, just for sure larger. And then I can again make a t. In this case, can say, okay, the t will be this one. Now, if I now do the step here, that will take some time. Oh, I have to rewrite this. So let me run it from here. Excuse me. So let me run it from here. So I will do it like this. So I've done again the run, and you can see that the plot now doesn't show a sustained oscillation. So this system is stable. We have no out of control output. If I now make the k just smaller than what we had, so this number was actually what the limit was, so let's make it just -1, so it is directly much lower than that one. So again, if I just run and I have the plot, you can see that it is out of control. It goes in the inverted side, but it is very high value for already at 6 seconds. So we have now verified that we need a larger value of that one. You can verify this by also checking your PZ map. So you can say PZ map, and then I want to check that for the poles. That's also fine, pole for T. So you can see numerically what your poles are. This is a stable pole, but these two poles will produce an unstable system. If I again make this just -29/66, again run this for the marginal stable system, you can see what the poles are. Now we are not interested in the plot at the moment, so pole and then t. And you can see that there is a -11 as a pure real pole, which is a stable pole, but these are two pure imaginary poles, and there's a pole pair, so this will of course produce a oscillation. Now again, I can also check for -1, which is I mean the +1, which is now the stable condition. So again, pole and then the poles for t. We can see that all of them have a negative real value. That means that we have for sure a stable system. Now we have verified that our system is stable for k larger than -29/66. And we have also determined our oscillation frequency using the auxiliary polynomial in our Routh table, and from there we have also determined our oscillation period, which is 2.78 on our calculation, and we have now found here 2.8, of course, with the rounding of errors also for determining the plot. Okay guys, it was for this example. Again, a complete example with calculations and a lot of discussion around it, and also the simulation to verify our calculations. If you have questions, comments, please let me know and I will try to answer them as soon as possible. Thank you very much again for your attention and have a nice day. Take care.